Hi, everyone. My name is Adam Baer. I'm a postdoc at Harvard University. And today I'm going to talk about some work I've been doing with my PI, Fiery Cushman, about how loss functions modulate the optimal bias-variance trade-off. So imagine you're coaching the following unusual game of darts, which has 2 rounds. In the first round, your dart thrower is trying to hit the target and gets rewarded according to this payoff scheme depicted in the diagram. Round 2, however, is considerably more difficult than this, where your dart thrower only gets rewarded if he's very close to the target, and even minor deviations from that can result in 0 points. Now imagine you have 2 pairs you can put in for these 2 rounds. The first, who we'll call Lefty, is quite consistent in his shots. However, he systematically always shoots a bit to the left of the target. Lucy, on the other hand, is not systematically off target, so the average of her throws is right on the bullseye. However, from throw to throw, she can be quite sporadic. Think for a moment about which of these people you'd want for each of these 2 rounds of the game. Well, here's one version of what might happen. As you can see, Lefty's systematic trend to throw to the left leads him to score considerably higher points than Lucy in round 1, because approximate sort of throws in this case are fine. However, Lefty performs abysmally in round 2, and Lucy, because she occasionally hits right near the target, ends up performing better. Today, I want to talk about how Lefty and Lucy represent 2 sources of error, which are apply more generally to a lot of interesting problems in the real world that we care about. The first kind of error, which is called bias, is represented by Lefty's sort of systematic average throw being off from the target. And in prediction problems, this kind of error can result from what's called underfitting your data. So in a prediction problem, we have some training data that we fit some algorithm to, and then we try to generalize that to new data. However, if our algorithm is too simple, as I'll explain on the next page, we can end up underfitting the data, and this leads to this systematic type of error. There's also, however, this other kind of error represented by Lucy's throws, which is unsystematic. So on average, there's not a systematic deviation from the target. However, if our algorithm is very sensitive to the training data, the algorithm ends up picking up on noise in the training data as well as the signal that we're trying to generalize to. And this results to this unsystematic kind of deviation from the target from different versions of the training data. And there's a familiar trade-off that arises in machine learning based on model complexity that shows that basically as you typically increase your model complexity, the unsystematic error known as the variance goes up, whereas the bias goes down, and the opposite is true as you reduce model complexity. So when thinking about a simple metric like mean squared error, bias squared and variance add up along with some irreducible error to produce the total error. And the goal is to minimize both at the same time and find this kind of Goldilocks zone where model complexity is neither too complex nor too simple. This trade-off is really important for many different contexts of prediction. And I don't have time to go into all of them, but I'll just give you a couple interesting examples. So first, from this interesting blog post of Scott Fortman-Rowe, shows what might happen if you're trying to predict political orientation, blue being Democrat, red being Republican, on the basis of religiosity and wealth. So imagine this data here is our training data. And now for new points in this grid, we want to be able to say, is this new person more likely to be a Democrat or Republican using our training data? So one very common algorithm is called K nearest neighbors, where what we do is we look for this new person, we look at people in our training data in the neighborhood of that new person and make a prediction about this new person on the basis of the people close to him in the training data. So what happens if we use a K of 1, meaning we just look to a single person in the neighborhood closest to the person we're predicting? As you can see in the top left, what results is a very kind of irregular pattern of red and blue predictions that clearly overfits the data. So there's clearly a lot of noise here from the training data where there are these patches of red and blue that aren't capturing true regularities in the world as represented by that dotted black line. On the opposite extreme, in the image in the bottom right, you see what happens if you use a lot of neighbors, in this case 80 neighbors, to make a classification for one novel individual. What you see is that the function ends up being very smooth, but too smooth, and so you get bias away from this dotted black line. Ideally, we want to find the point in the middle, in this case, maybe around k of 20, that captures both the regularities but doesn't overfit. This also arises for function approximation when we're doing, for example, simple regression. We can use simple functions like just a line as represented on the left. This can sometimes lead to bias where we're missing out on important regularities, but there's limited variance from moving from different iterations of our training data. Whereas fitting really complex polynomials will lower our bias. However, it will lead to wildly different predictions based on different versions of the training data and lead to this harmful variance. There are many more examples that I could go into, but I want to talk today about applications to cognitive science and psychology. And we're not the first to bring up how the bias-variance trade-off might be useful here. Gerd Gigerenzer has made the point in the context of the judgment and heuristics research program that was started by Kahneman and Tversky, that there's perhaps too much of an emphasis on bias and not enough of an emphasis on variance when thinking about what humans should optimally be doing. So he argues there's a bias to focus on bias and not focus enough on variance. And this leads researchers like Kahneman and Tversky to criticize ordinary people for using biased heuristics to solve problems without evaluating whether those biased heuristics might actually outperform more complex decision strategies, which might be susceptible to larger unsystematic noise or variance. And we want to build on this question today. We want to particularly ask, when might the simple high bias strategies as represented by heuristics or other simple cognitive abilities be preferable to using more complex high variance ones? And Gigerenzer has already given us some indication that when data is sparse or noisy, it makes sense to use heuristics because there's a smaller signal to noise ratio. We want to add an additional interesting hypothesis, which is that perhaps not just the amount of data you have, but the structure of your prediction problem, and particularly your objective function, which we'll refer to as the loss function, which is the negative of utility, matters. And in particular, there's this property of convexity we think is particularly relevant to answering this problem. What do we mean by convexity? Well, let's come back to the diagram from the beginning. So in round one, it seemed like being relatively close to the target as opposed to being really far off the target was really important. But being exactly right was not particularly important relative to being a little bit off, right? And this is what we mean by convex loss, where approximate solutions are okay if you're in the neighborhood of the right answer. However, extreme errors can cost you a lot relative to moderate errors. In contrast, a concave loss function has the opposite structure, where errors make a really big difference when you're very close to the target. So being exactly right versus being a little bit wrong makes a huge difference to your payoffs, whereas being extremely wrong or moderately wrong makes very little difference, as shown by the fact that Lefty, even though he is generally closer to the target than Lucy's for other throws, nevertheless ends up with 0 points. We want to explore this in a little more detail with some numerical simulations. So what we do is we consider some different loss functions that are smooth in different contexts. So the first types of loss functions we'll consider are just power functions. So just saying as you as your error increases, your loss increases to raise to some power. So 1/2 would mean a square root error. Power 2 would be the common mean squared error. Power 3 would be even more convex than that, where large deviations really matter. And if you care about the math, you can think of the magnitude of the second derivative when this function is positive as indicating what we mean by convexity, where larger second derivatives are more convex in our language. We also consider some other functions, like the logarithmic function, which is highly concave, versus the exponential, which is highly convex. And this local mass function, which has convexity and concavity at different points in the function, and is kind of like an inverted bell curve. So how do we analyze the bias-variance trade-off? We do this in a very general way by assuming that prediction error follows a Gaussian or normal distribution, where ideally you want to be, you want to minimize this prediction error and get 0. So the mean of this Gaussian is beta, which is our bias in the machine learning language. And the variance is, of course, variance. And we're computing expected loss by just getting the area under the curve of the product of loss with these probabilities. And if you prefer to think about expected utility, just take the negative of the loss function, and then that's just like the common expected utility function. So what I'm going to show you here first is the power loss functions. Recall that the higher plots represent more concave loss functions, where you want to emphasize being exactly right according to our theory, whereas higher powers, like power of 3 at the bottom, are cases with highly convex loss functions, where we think approximate solutions will outperform simpler ones. Will outperform more complex ones. So what I'm showing you in these surface plots here is the expected loss represented by the redness of different points, where redness is something you want to avoid, and you'd ideally be in the bluer points. And I'm plotting on the x-axis the bias, and on the y-axis the square root of variance. So these things are kind of uncomparable units. And these white isoclines represent points of equal expected loss along this bias-variance trade-off. If you follow these isoclines perpendicular on these green lines that we're plotting here, you can get an indication of the sort of optimal bias-variance trade-off given some constraint, where shallower green lines indicate that bias is relatively less costly than variance, and the opposite is true for more steep green lines. So what we find is exactly what we predicted. So at the top, when the loss function is more concave, variance seems to be less costly than bias. That is, Lucy-like strategy seems to perform better than a lefty-like strategy. But we find the opposite in the case where the loss function becomes more convex. There, it seems like an approximate bias solution with limited variance would outperform a high variance one. We can see this also if we plot the standard deviation on the x-axis and expected loss on the y-axis for different bias values. And an interesting feature of this, which has been pointed out in earlier literature, is that for concave loss functions, actually, like the one on top, you see that variance not only isn't always very harmful, but actually can be helpful if your bias is large. So if Lefty added a little bit of variance to his strategy in the concave case in that round 2, he actually would have performed better, because maybe he would have just inadvertently hit the bullseye. That's the idea. I'll show you just briefly these other loss functions we considered. We find more or less the exact same trend as we'd expected, where for the more concave functions of local mass and logarithmic, there it seems like precision and high variance are preferred to approximate bias solutions, but the opposite is very much true for the exponential function, where variance is increasingly costly. And again, we see this interesting interaction between variance and bias, where variance can actually help you when bias is large. So our ultimate goal is to connect this back to cognitive science, and we're doing some ongoing work to explore this. Broadly speaking, we think that these convex loss domains, where it seems like approximate solutions might be better, might be associated with what Kahneman and Tversky would call system 1, these more automatic simple cognitions. Whereas concave loss domains, where you really want to be exactly right, might be represented by system 2 or more deliberative situations. But there are some more kind of specific predictions we might have in mind for how bias and variance might apply to psychology. For one thing, you might think this would come up in comparing model-free versus model-based decision algorithms or prediction algorithms. For example, imagine you're trying to anticipate what you would want to eat for dinner today. So a biased simple solution, a model-free solution, might just look at the average of what you've liked best in the past. that's going to be biased because your preferences might change over time or be dependent on what you ate yesterday and other things like that. So you could instead approximate a more complex generative model using a model-based algorithm, but that will lead to more variance. So there's an interesting bias-variance trade-off there. There also seems to be a bias-variance trade-off in the context of comparing social or imitation-based learning with more individual learning, where imitation-based learning lets you draw on a lot more data, sort of like the k nearest neighbors algorithm with high k values. However, that can bias your decisions or predictions because you're drawing on data that might not be super relevant to the problem in hand. Finally, you can think about generally systems in the brain that have learned slow versus fast. Slow learning systems, perhaps, that have been developed over thousands of years via genetic evolution or hundreds of years via cultural evolution. Those are going to be able to use a lot more data, but end up being more biased, perhaps, than these fast learning systems that use conscious updating that could learn in as fast as a few seconds or minutes. However, you're relying on less data in that case and perhaps are more susceptible to higher variance. And with that, I'll wrap up and say thank you very much.